goes as follows. The probability of A given B equals the probability of B given A times the probability of A over the probability of B. To explain, we will use a problem that involves coins. Let's say you have one fair coin and one biased coin. These represent the start of our branch patterns to show probability. Next, we draw branches that represent the outcomes of flipping each of these coins and the probabilities of the outcomes. For the fair coin, you have 1 out of 2 chance of flipping heads and another branch that represents flipping tails. For the biased coin, let's say there is a 2 in 3 chance of flipping tails. So you would have 2 branches that represent tails and 1 that represents heads. Now to compare these 2 coins, you need the same number of branches on each side. So you would use least common multiples, which would be 6 between this 2 and those 3 branches, to draw the right number of branches. You should now have 6 branches on either side. It's important to still keep the outcomes in the right proportions, however, so that you have the right probabilities when you go to work with them. Now, we know that we have a 1 in 2 chance of randomly picking the fair coin or the biased coin if they're just sitting in a bag together. So if we pick a coin and flip it, let's say it lands heads, and we don't really know if it's the fair coin or the biased coin yet. Because the coin landed heads, we can cut all the branches that lead to tails. So now we're just focusing on these 2 branches over here and these 3 over here, because we know it landed on heads. Now we want to find the probability that this was the biased coin that we flipped. Because there are 2 branches over here from the biased coin that lead to heads, and 3 branches over here from the fair coin that leads to heads, we know that there is a 2 in 5 total chance that we just flipped the biased coin.
Now let's use the equation. So we know that the coin landed on heads. So that's our given, or our B. And our assumption is that it's the biased coin that was chosen out of the bag. So that's A. So we're trying to find the probability of it being the biased coin given that it landed on heads. So now let's plug some numbers into this equation. The first number we need is the probability of the outcome being heads if the coin is biased, which is 2 out of 6 or 1 out of 3. So let's use 1 out of 3. And we multiply that by the probability that the coin we picked is biased, which is 1 out of 2, or 1/2. So we plug that in. And next we divide those 2 numbers by the probability that we flip heads, which is 5 out of 12. And when you multiply these 2 numbers together and divide, you get 2/5, which is the probability that we flipped the biased coin.
Now that we know that the theorem works, let's try it out. Here's an example problem. 15% of all people in a given population have blonde hair. 5% of people in that population have blue eyes. 50% of the people with blue eyes have blonde hair. What is the probability that a person in that population with blonde hair has blue eyes? First, let's match our variables to our information. Our information is listed on the right. The probability that a person has blue eyes is 5%, or 0.05. The probability that a person has blonde hair is 15%, or 0.15. The probability that a person with blue eyes has blonde hair is 50%, or 0.5. Then, the probability that a person with blonde hair has blue eyes is unknown. Now, let's look at our variables. The first variable is the probability of A given B. This is what Bayes' theorem will eventually tell us, so it's our unknown, or the probability that a person with blonde hair has blue eyes. Next, is the probability of B given A, which is basically the reverse of the first one. So this would correspond to a person with blue eyes having blonde hair. Now, the probability of A, or what we're searching for in the first variable, which would be blue eyes. Next, the probability of B would be a person having blonde hair. Now, let's plug our variables into the equation to find the answer. So, the probability that a person with blonde hair has blue eyes is the probability of B given A times the probability of A over the probability of B. Plug this into a calculator and you'll get that the probability of a person with blonde hair having blue eyes is 16.66666%, or 1 in 6.